larger and lower than is there any way you can make it fast enough to get around? Is there so much? Part of it is because there's so much overhead.
Okay, welcome back. So today I'm going to have a slightly different format for our lecture. It'll sort of tie up some of the issues of transmission lines, but it'll also move into other types of plane waves as well. Just a completely different perspective on some of the things we've been talking about and other directions as well. Before I do that, I do want to remind you and our audience at home of the midterm that's a week from Wednesday. And the material will cover up to last Wednesday, the end of transmission lines, basically. And so Wednesday, November 5th is our midterm in this room. It'll be closed book, no notes, no calculator. Yeah, so probably 3 questions. I will probably reverse the no notes a little bit on the final. Just to remind you that we will also have a test on the last day of class on homework and the computer project, which is also out there. And then the final will be the usual time, official place. Okay? Any questions about that? Good. All right. So let's have some fun tonight. So there's a classic problem called the Etalon or the Fabry-Perot Etalon problem in ion optics. I don't know how many people have heard of that. Has anyone? Okay. Well, it's a transmission line. And remember what we did with our transmission lines was we had one boundary. Oops, that's not supposed to happen. There we go. We had one boundary, and then our transmission line went on forever and ever. Or our plane wave interacted with the dielectric, and the dielectric was semi-infinite, so it went on forever and ever and ever and ever, and never stopped. Well, the question is, what happens? Hang on, I want to erase that. What happens if I've got one boundary and then another boundary? And so you can look at this as two mirrors facing each other, or one plate of glass that's nicely straight. And the way I'd like to approach this problem, the first time I'd like to approach this problem is I'd like to say, okay, supposing I have a short pulse, and what I mean by that short pulse is that this width of this pulse is much less in time than the round trip of that cavity, of that little structure, of that Etalon structure. Okay? And so what will happen is this pulse will come in, and it'll see the first mirror, and the first mirror has a finite reflectivity. And so part of it will get reflected, part of it will go into the Etalon. It'll come back out. It's short. This is a short pulse relative to the round trip. So it'll propagate, hit the back mirror, and then it'll come out. So I'll have 2 pulses, but they'll be delayed by a time 2L over C. Okay? And and then by the way, this will also bounce again, and a third pulse will come out, and I'll have an infinite number of echoes. Okay? I don't know quite yet how the screen works, so bear with me on that a little bit. Whoops. All right. So we have multiple pulses coming out. And the first one will have an intensity I1, the second one will have intensity I2, and the third one will have intensity I3. And if you've been watching my scribbling, the first one will be proportional to the mirror reflectivity R1. The second one will be 2 transmission passes, which in power is 1 minus R1 quantity squared. The third one will have 2 transmission passes, but a reflection and also we'll have a third 1 minus R3. And then for fun, we can ask what happens if these 2 guys are the same height. Okay, what do we need to have for that? There's got to be a way to clear that off, other than this. All right. Well, if that's the case, then I have R1 is equal to 1 minus R1 squared. This is a trivial quadratic formula problem. And I'm left with an R1 is equal to 3 plus or minus the square root of 5 over 2. Some of you might recognize that from golden mean type of applications if you're sort of a high school math nerd. And so we look at R1 must be between 0 and 1. And that means that the 3 plus the square root of 5 is too big, even when you divide by 2. So we want the minus sign. And what that gives you is a little bit less than 40%, 38.2. Okay, and that is a mathematically famous number. And again, it's related to Fibonacci series, and it's related to the golden mean. So here's sort of what we did. If we here's the mathematics. If we add up 1 and 2, we see that we want only those two pulses. We can say that structure is 76% efficient, and the rest of the energy is in that tail of pulses after the first two pulses. So what I've done is I've used two mirrors, 1 degree of freedom, to make one pulse into two pulses. Okay, and that's actually a useful device. I can continue on this path. Okay, I can continue to add mirrors together. And what this is this might be transmission line 1 at 50 ohms, plus another one at 60 ohms, plus another one at 50 ohms, and so on down the line, so that I've got multiple reflections of these short, sharp pulses between the two. And you can see the I naught coming in, and here's my first out, I1. My second one does the same thing that we had before. It goes into the structure, it bounces off of R2 and comes back out and gives me a pulse at I2. The third one comes in, and this was a little bit different. This snakes around and comes back out as I3. The fourth one, I've got two ways of getting there. I can go all the way, I can serpentine around here, or I can spend more time in here, or I can spend more time in here, or I can go all the way through. So I have a much more complicated sum to get me my I3 and my I4 and so on. So these are just lumps of energy, there's no waves underneath them for constructive or destructive interference, or they add up over time in an average way, we can write down the equations just purely in power. I1 is equal to R1, I2 is equal to 1 minus R1 squared times R2, I3 is equal to 1 minus R1 squared, 1 minus R2 squared times R3, and then here's the general formula for the nth pulse as a function with the mirrors. And then if I have a set of equations, I can say, well, I want as many mirrors I have, as many degrees of freedom I have, those are the number of pulses that I want to be the same. So I'm generating a burst of pulses that are exactly the same in height. So I set my intensities equal to 0 and equal to each other. And I have this set of equations. I have R1 equal to 1. That's just one mirror. For two mirrors, I have the equation that we had before. For three mirrors, I have this one. And then I can continue to go up. And my polynomials actually start... If I solve these polynomials, I'll solve for the mirrors, and I can unravel and I can find out what the magic reflectivities are that will give me pulse after pulse after pulse after pulse to be all the same. This is a math trick. This is a fun little thing. Although we can build it in transmission lines, we can build it in optics, we can build it in plane waves and what have you. Okay? Or pulses at least, and so on. And so this way we can build up the formula. Now, there's also some nice structure. You'll see 1, minus 3, 1. You'll see 1, minus 7, 13, minus 7, 1. And your polynomials, 1, minus 15, here's the minus 15, 83, 83, 220, minus 220, minus 220, and 303. So there's a symmetry on these polynomials. And it was only a few years ago that this mathematician discovered this paper, these results, and actually formalized it as a problem of series solutions that he was able to decode the formula to generate these polynomials independently of the structure. And so here's the general formula for that. I can also go ahead and I can add interference. So these are optical pulses or electromagnetic pulses. So they have an envelope of energy. They have an envelope of energy, and then underneath it, they've got a packet of the waveform. And if I add up two of these, I can either add them up in phase, or I can add them up out of phase, destructive interference. And so that's the difference between adding a plus and adding a minus in these sets of equations. But nonetheless, we can go ahead and, to our heart's content, do the calculations. Nothing's more fun than a little bit of algebra. And so we can come up with the reflectivities for the incoherent case, for the constructive case, and for the destructive case. And you see that they shift over just a little bit, as you would expect. They shift around, the coefficients of these mirrors shift around a little bit. And the efficiencies go down as you lose the coherence or the constructive interference. And that makes some sort of sense as well. So here's the... And then if we go up to a 1, 2, 3, 4, 5, 6, 7 set of pulses, we can go ahead and calculate the mirror reflectivities for this. And in fact, we've built these years ago in the lab. We've sent a short pulse in there, and we generated streams of pulses that were approaching a terahertz of frequency content, of pulse repetition frequency. So that's quite fast, and especially in those days, there wasn't. For a while, we held the record for pulse trains, just using these kinds of simple devices. And I called these optical rattlers because the light rattled back and forth between the mirrors before leaking out. Okay, and once you get to a certain level of complexity, this algebra gets kind of out of hand. So I used to. This was way back before modern computers. Back in the 90s, I used to race Mathematica. And occasionally I'd be able to do the algebra faster than Mathematica could do it. It was great fun, nice sport. I don't think I could do it now for many reasons. But here's populating tables like this, and then developing the mirror structures that do that. We made for fun projects. Now, so we also had some fun, and we did. This is for all pulses are the same amplitude. Here's a 1011, which is a Barker code, and here's a 1, 2, 3, 4, so a sawtooth waveform. And you can go through and you can continue to calculate mirror reflectivities for that. And then you can also do multipliers. You have to. I'll show you exactly how to do this, but you have to put your mirror at exactly the right distance, sort of halfway between if you have a stream of pulses coming in, not just one pulse, but a stream of pulses, and you put a mirror right at half the length, you can double your frequency, or triple it, or quadruple it, or all the way up to eightfold. And here are the mirror reflectivities that you'd have to do. So here's some experimental results. This pulse. This is a set of pulse trains, and it's instructive to look at the timeline here. This is measured in picoseconds, so distance between pulses is just a couple of picoseconds long. Okay, just a little bit under a picoseconds long, and that's so fast that you can't measure it on any oscilloscope. What you have to do is you have to generate a second harmonic, put two of these together, and do a cross correlation between the pulses and look at the nonlinear response in a crystal. So this is the number of photons for the second harmonic generation of this. And you can see that with the right mirror reflectivities, we do a pretty good job of getting the four pulses to line up, and then we see the exponential decay behind it. Okay? So the structure here, we're coming in with a short, sharp pulse, and we're seeing a train of pulses come out of that. Okay? Remember the sawtooth? Well, we did the ramp. And if you connect the dots, that's a pretty nice linear line. And again, after we run out of degrees of freedom, we have our decay. Here's our coded pulse, a 1011. And then we the step function or the uniform one. If we sent this back into the same filter, we would take one pulse. We'd go into a step. We would come up with a step function, and then we'd come up again with a ramp. And so we're doing simple integration. Okay. And then again, if we did the same thing back into the same filter, this is getting a little bit beyond our control, but we begin to get a quadratic rise in that. Okay? And again, all this processing is done at a tremendously fast rate. Okay? So now if we, instead of a single pulse, if we come in with a train of pulses, and so we have just a stream of pulses, they're all separated by a period capital T, and then I make this device here so that the round trip time is half of T. What I'll end up doing is I'll end up borrowing some of this pulse and putting it in the dark space between the pulses. But because of the infinite nature of these tails, some of the pulse will also go there, and even a little bit all the way down the line. So it's not just a question of taking half this power and putting it here, because I have a residue that adds up. So I have to do this calculation kind of carefully if I want a nice, smooth, even train of pulses at twice the frequency of my mode lock laser that I was working with. So this is sort of an interesting problem to work out. And the way I ended up finally doing this was I said, okay, I've got an instant of time where I've got an input pulse going into my etalon, going into my two mirrors. There's a mirror, and there's a mirror. And at that time, I've got a collision of two bodies. I've got an input pulse, and I've got a residual pulse that's rattling around inside of it, and they're both colliding with the mirror to create products. Okay? To create products. So I don't know this amplitude, but I called the amplitude of this residual pulse X, and the input pulse I think had an amplitude of 1. And I called my two products I1. A type 1 collision produces a usable I1, and then the output, this residual here, I called this guy Y. Okay. And what Y does is Y goes around and rattles off against the R2 mirror, and comes back around to interact with the partially reflecting mirror R1 in the dark space between the pulses, the input pulses. Okay? So I call this a sort of a type 2 collision, where I have a pulse Y coming in and giving an output product of I2. Okay? And then this Y, you may note, comes back around and becomes the X for the next type of collision. Okay? And this sort of moving reference frame is kind of a nice way of solving the problem, solving the algebra. It was reminiscent to me of the moving reference frame of the transmission line problem that we solved a couple lectures ago. And in any event, it makes me happy because I can come up with very nice set of equations, very nice simple set of equations that govern this doubling of the pulse repetition frequency. I have the output product 1 is equal to R. That's the reflected off of the first mirror, plus the product X that filters through the 1 minus R. And then I have the simple I2 is just whatever y is multiplied by the transmission function of that mirror. And then I have x is equal to yr, and I have y is equal to xr plus y. Those are my right-hand products. And I can solve these guys, plug them back in, and I can get an answer for I1 in terms of r, and I2 in terms of r. And if I solve these guys together, something comforting, I get an r equal 1/3. Okay? So kind of a nice answer for this pulse repetition frequency multiplier by a factor of 2. Okay? And if I plot what my modulation depth is as a function of the reflection coefficient, I see my minimum modulation depth right around 1/3, and you'll notice how sharp at any small little deviation from it, and I shoot way up to I go down to I'm off by 10%, and I have a 10% modulation depth. So that's not very. That then requires some quite precision numbers on that. Here's the experimental setup that we did. It's an old clunky mode lock laser. The problem to solve was that everything was governed. The pulse repetition rate was governed by the spacings of those two mirrors, which in turn was governed by the time dynamics of the gain system and the other lasers. And the typical number here is 82 to 100 megahertz. It was easy to go down in frequency. It was very hard to go up in frequency. So we wanted to go to 200 megahertz, 400 megahertz, and so on. And that's where we put in this optical rattler. Okay, and we looked at it in with a variety of instruments. The particular one is just an oscilloscope because even though we can't resolve the short picosecond pulse, we can resolve the 82 to 100 megahertz rep rate pretty well on a fast scope. And here is our. You can see how old these are. These are actually oscilloscope pictures. Nowadays, you just plot them out, and you wouldn't even be able to tell it was real data. So there's something kind of nice and old school about this. But you can see that the waveform has a pretty nice flat line, and then we double it, and you can see a little bit of modulation depth, but not too bad for our thing. And then we even quadrupled it with appropriate design. So very simple, very fun, nice little algebra. Here's some other experiments that we did. 4x multiplication, 8x multiplication. And it gets really shabby. With 8x multiplication, again, all the errors sort of start creeping in on you. And, there are other configurations that'll do this. This is a particularly nice one because you can implement it all with, in stages, all with the same type of mirror. So once you start thinking about solving this problem, and here's one that might actually ring a bell with you, right? You can have a delay line, an input, and your first delay line comes here. Your second output follows this path. Your third output follows this path. That structure might ring a bell, or that image might ring a bell to some of the people who do filter theory. And that's exactly where I'm going with this lecture. Okay. And anyway, there's a variety of these structures that solve this problem, and this problem is not necessarily all that obscure. It comes up a lot when you're working with pulse trains in lasers. Okay. So now what I want to do is I want to give you that's my precursor, and that's sort of how I started getting into this field of I had a practical laser, I had a practical problem. I wanted to up the repetition rate of this laser at very, very high rates, and also at multiples of the inherent natural rate of the laser. So I'll take a giant step backwards, and I'll give you this next couple of slides actually belongs in a course like this. It is your classic graduate school approach to something called a Fabry-Perot etalon. Okay, and in this Fabry-Perot etalon, I have a mirror with a reflectivity right-left, and reflection on the left side, transmission on the left side, reflection on the right side, reflection on the left side. It's two mirrors spaced L, or one transmission line that's improperly terminated. That's another point. So I have a sine wave coming in, a plane wave coming in here, and I have a plane wave reflected out here, and I have some plane wave that leaks out the other side. Okay. So this is a plane wave hitting a dielectric surface, but the dielectric has another surface, has a back surface. So it's like a piece of window glass. Okay, but it's rather precise window glass because there's no tilt on any of these elements. Okay, so you have to kind of play around to make sure that they're flat and parallel. And if you solve the wave equation, which we've done a million times, you get the plane wave term if k is just a constant here. Then we pull k out of the integral, and this whole thing becomes a ikz. Okay? This is a nice integral just in case you've loaded your cavity with some material, and then that material might change its density across there. Your phase shift will change, but more gradually, but you still add up to the same number of clock cycles. Okay, so that just gives you a little bit more. That's your plane wave, but it's just a slightly more general state of that. So in steady state, and we're going to try to figure out what this guy is. In steady state, I'm going to have a wave that comes out straight through. I'm going to have a wave that's delayed, another wave that's delayed, and because I'm loading this with a sine wave, a plane wave, a continuous plane wave, the relative phase of each of these outputs matters. Okay? So I may be in complete coherence, complete constructive interference, complete destructive interference, or somewhere in between. Okay? So I'm adding up, I'm doing a superposition of all these plane waves on the output, and I'm adding them up given their amplitude, which are determined by these guys, and whether they're in phase or not, which is determined by the propagation delay of the cavity. Okay? So I'm left with an infinite sum. My first term is transmission on the left, transmission on the right, the input value of my electric field, and the relative phase shift that the structure gives it. Okay? The second wave through is the transmission on the left-hand side, a reflection on the right-hand side, a reflection off of the left-hand side, a transmission on the right-hand side, and then twice the phase delay. The third guy through, transmission on the left-hand side, reflection on the right, reflection on the left, reflection on the right, reflection on the left, reflection on the right, transmission on the right, and 3 phase delays of my structure through there. And so I can write this. It's an infinite sum. And so I collect out all the common terms. And I'm left with this 1 plus 1 phase shift plus 2 phase shifts and so on all the way out to infinity. And then I have these products of R1 and R2, or R left and R right. Remember, those are less than 1. And they're being raised to a new power as I go down in this series. So It's the binomial theorem. It's 1 plus x squared plus x cubed and so on, and it converges to 1 over 1 minus x. Okay? That's one of those summation rules that you've probably seen in a bunch of courses, and if you're like me, you always forget it. Okay? And that's sort of the conventional way of solving this Fabry-Perot-Etalon, or Fabry-Perot transmission line. If I put everything back in for x, here's my transmitted as a function of my input field. If I multiply through by complex conjugate and come up with the intensities, I have an intensity transmitted over an intensity input. The factor in front is t squared over 1 minus r squared. And then this parameter here is 1 over 1 plus 4r over 1 plus r squared. And then here's my phase term here, whether or not I'm adding constructively or destructively. And so this is my resonance denominator. You can see that if sine is equal to minus 1, my denominator gets smaller and my intensity transmitted goes up. So at very particular values of delta, I will have a resonance condition where I will have a maximum constructive interference and more light will come out rather than when I'm off resonance. Okay? And the peaks occur when the propagation constant k, that's 2 pi over lambda, remember, is equal to some integer multiplied by pi over L. And the distance between these two peaks in optics is called a free spectral range. And it occurs at C over 2nL. Okay? So when an integer number of wavelengths is equal to L, I have this free spectral range. Okay? And that is that's sort of your classic presentation of your Fabry-Perot-Etalon. Again, 2 mirrors. And if you think about what I did in the initial part of this lecture, where you guys were all shaking your heads saying, what the heck am I doing? I was analyzing this Fabry-Perot-Etalon. But instead of looking at the sine wave input, what I was doing was I was putting a short, sharp spike into it. Right? And if I didn't tell you that was a mode-locked laser pulse, what the impression that you would have gotten, quite rightly, is that's my delta function loading, and this is my sinusoidal loading. Okay? So so now what we're doing is we're looking at this block of glass, this empty transmission line, this set of this window glass, and we're saying, gee, I'm able to sort colors, I'm able to sort wavelengths, the wavelengths that add up in phase. Where is that? Integer number of wavelengths. Those guys go through this device. The wavelengths that don't add up in phase, they get rejected by the device. Okay, that's a sinusoidal argument. But regardless, it's the same structure. And I should be able to excite that structure if I remember my signals and systems, which I better because I'm teaching it this semester. I should be able to excite that system with whatever function I want. And as long as I know something about that structure, I should be able to calculate the output. Okay? In other words, this block of glass is linear. It's time invariant. It's a filter. Okay? And what I did at the beginning of the class, when I excited it with my delta function, I was looking for my impulse function response h of t. Okay? So once I have that, I fully characterize the system. And further, there's got to be a better way to clean this. I'm afraid to press too many buttons. Uh-oh, see, that's why I shouldn't do these things. Oh, dear. Oh, dear. Let's see. Now it doesn't like me at all. No. Go away. Smart Notebook, number 11. There. No, go away. All right. Anyway, that's going to come back to haunt me, I know it. All right. Yeah, don't let me play with any new toys of high tech that you care about. So if I look at this expression here, this is my filter response. Output over input. And has a resonance response, which we could actually categorize, if we want to, as a band pass filter. Okay? It happens to be an interesting filter because it cycles back on top of itself again and again and again. Now, so there's the classic picture. So let's see how we might structure this with a signal flow diagram. Okay? And we come in with an electric field on the input, and part of the light goes through the glass and comes back out. Okay? Part of it gets reflected. So part of the light comes in, it gets reflected, part of it goes part of it, and then part of it comes back out at you. Sorry, hang on 1 second. These. Okay, so I have I've got an input signal here, and there's a transmission through the first mirror. There's a delay, transmission through the second mirror, and there's part of the output there. Okay. In addition, there's a reflected component, and the reflected component just sees a reflection coefficient and comes back out a different output. Okay. Now the signal that goes goes through the device has a probability, or with its reflection coefficient, part of it will be reflected, fed back, going through a delay, coming back out, and being reflected and joining the reflected wave. Or it can be reflected by the front mirror, join that signal, see another delay, and go on its way down that way. So there's my infinite loop inside of there. Okay? Notice that what I've done is, instead of writing the z to the I delta, which is perfectly reasonable, I've written this in terms of z to the minus 1, so I've made use of the z transform. So what I've done is, in the same way that you would take an LRC circuit and use your 1 over j omega c or your j omega l's and convert those differential equations on the diagram to an algebraic diagram in frequency space, what I've done is I've taken these delays and the infinite sum, and I've converted it to just algebra in the z domain. Okay? So instead of going into the frequency domain, the continuous time frequency domain, I've gone into the discrete time frequency domain. And again, the reason I was inspired to do that is because of these delta functions coming in and a stream of delta functions coming back out with set delays. Okay? And so that looks to me very much like a digital filter or a discrete time filter instead of a continuous time filter. The advantage is as soon as I use the Z transform, I automatically make use of all the discrete time signal processing packages, notably MATLAB. Okay? And by the way, we already said that a delay can be written in the Z transform notation as that, or in the continuous time world as that. So I can go back and forth at the end. I can go back and forth from the Z transform to the Fourier transform anytime I want to. Okay, so there's more in common with those two transforms than not. In this, okay? So there's a number of reasons why you write it this way. You're explicitly saying what the delay is. The delay is the transit time through the transmission line or through the block of glass, and this structure. And now all of a sudden you can instantly categorize this filter. It's an IIR, infinite impulse response feedback based filter of order 1. Okay, so as soon as you draw the signal flow diagram, what you do is you immediately move from the optics of the problem, or if you're doing a transmission line, a single transmission line, the electromagnetics of the problem, and you go into a filter space. And you pick up all the software tools that you need with MATLAB, right? So you join the ranks of filter designers as opposed to Smith chart, folks, or physics students doing infinite sums. Okay, and so just to show you what the algebra is, I have an input signal, I have an output signal. I have the transmitted signal, and I find it useful to introduce an intermediate signal. That just helps keep my algebra a little bit more sane, or my writing a little bit more sane. So here's my structure. I come up with these equations of state. So I have an input, reflection coefficient, giving me a part of my reflected output. The initial input, well, actually let me hold off on that for just a heartbeat. If you come back and you take a look at where A is, you'll see that A gets delayed, reflected back, gets delayed, and joins up with that ER. So ER is equal to A coming down this path and E going down this path. Okay? And so here is my blue path and here is my red path to give me my ER. Two nice simple terms in Z space instead of an infinite sum in time space. Okay? That's huge. Maybe not so much for the Fabry-Perot etalon, but when we want to do better than a Fabry-Perot etalon, when we want to do higher order filters, not just single pole filters, but higher order filters, that kind of benefit accrues tremendously. Okay, and so if you spend a little bit of time, you have to write an equation of motion for A. A comprises this guy here, and it also comprises what it used to be after coming back on that loop. And so those two terms, again, the first one, and then in terms of itself there. And then the output on the transmission is just a simple function of A. Okay? So these are our equations of motion, or I call these equations of state. as in state space analysis. I know some of you have studied that. How do I get rid of this? Ugh. It's such a nice podium. I wish I knew how to run it. Well,
You can even move the mouse.
I don't want to use the mouse.
But, yeah, where it was sitting.
I mean, I can scroll down this way, but I want to get rid of this guy.
Right. Move the mouse away from it,
Okay.
and then just leave it be.
Okay. That's not good. All right. All right. So, if I solve these algebraic equations, I eliminate A. It's simple, just simple algebra. For now, I'm left with a transfer function in transmission and a transfer function in reflection. And if you squint your eyes and you take a look at this term here, e to the I delta, you can imagine through Euler's relationship and cleaning things up that will give you your exactly your resonance denominator, as we had before. Okay? And then we have a different transmission function for reflection. This is a filter, but it's a single input, double output filter. And so we have transfer functions in both of those cases, and both of them are second order. The way we've defined it. Okay, but it's a little bit odd because I don't have a first order term in the denominator, so I can reclock this digital filter if I want to. Okay. If I put this in rational form, here's my reflected versus my input, just putting everything over the same common denominator. Oh, now if you've had DSP, these are the polynomial in your numerator. I think those are the B coefficients, and the polynomial in the denominator, those are your A coefficients. You factor those to get your roots. And those are your resonance conditions, and so on. Okay, so this is exactly a digital filter description of the Fabry-Perot etalon, which means this is how you would describe it if you're doing it in MATLAB. Okay, if you want to continue down this path of going away from electromagnetics and more into digital discrete time signal processing, then you can come up with regions of convergence for stability. You can come up with difference equations where you write the inputs and the outputs in terms of delays. If you want to realize this transfer function in other architectures, you can factor it in cascade form. So you'll have a first filter cascaded with a second filter. Or you'll have it in parallel form. Like that. And this is the beginning of a primitive device called an AWG, arrayed waveguide, or a horn, if you want to think of it this way. Okay, so the idea of once you have these transfer functions, especially in Z-space, you can manipulate them around, and you can make the same filter, but you can realize it with different architectures. Okay. If you were working with a Smith chart, and I know many of you do, you can have a parallel shunt, or you can have a series shunt, both to do the same thing. Right, and so that's an analog to what we're doing here by rearranging the algebra. Okay, but remember what we're doing. The way we're doing this is we're all doing this in a computer package like MATLAB, which you guys learned sophomore year, or something like that. And so you're fairly facile at it. And then think about the Smith chart where you have to go around and around and think about what you're doing. What this does is this unlocks electromagnetics, transmission lines, photonic filter design to all the DSP people, right? So they don't need Smith charts to do any of these kinds of resonance because it's all keeping track of the poles and zeros in the linear algebra that describes structures like this. And the structures can be more... Oh, okay, so you can plot your transfer function. Here's your one free spectral range. Transmission here and here. Rejection there. That's just for arbitrary, not very good... not very good mirror selectivities. You have phase response. Again, all this terminology just pops right out of filters, but not commonly used in at least in the optical world, and certainly not this way. One thing that I like in filters, I'm not a big fan of phase response because phase is always normalized to a frequency. So what I would prefer is the question: how long does the wave stay in the structure? How long does the wave actually stay in the structure? And that answer for a given frequency, that answer is the group delay, which is the derivative of the phase response. Okay. So to me, the group delay measured in actual time is a little bit more meaningful than the phase response of a filter. But again, your mileage will vary. Depends on what you like to work with. But it just seems silly to normalize it with respect to a frequency that you're going to, and if you have a spread of frequencies that you're actually interested in. What's the phase response when you're off frequency? What does that really even mean? I can do the calculations, but this is so much more clean to me. There's a little formula for the thing. Now, like I said, once we have this algebra, we can now add mirrors. Remember that I was adding mirrors before with the delta function response or the multiplier response, and I had to think of some very complicated algebra tricks in order to be able to solve those problems. And I was wasting a ton of time, just doing the algebra by hand. Well, as soon as you have the signal flow diagram, you can add mirrors all day long to your structure, and the algebra just follows really mechanically. And it's perfectly amenable to a MATLAB implementation. So it's so nice and clean. And so in this case, what we have is we've got, I should have turned this around. We've got the first mirror, we've got a middle mirror, and then we've got the third mirror on the output. So this is a 3-mirror etalon or coupled etalon, or it's two transmission lines linked together between source and detector. So you can have all kinds of leaking back and forth, sloshing of the wave back and forth between one transmission line and another transmission line. And yes, it has a signal flow diagram that's exactly like what we constructed before with an extra stage. So if I look at this guy here, this is the first mirror, this is the middle mirror, this is the first transmission line or etalon. Delay, the mirror structure here. And now I have a mirror structure in the middle. And then I have delays for my second cavity before finally I have the output. Okay? To solve this, I still find it very convenient to introduce some intermediate variables. And so the intermediate variables are a signal that's going through transmission but is still in the first stage. A signal that's flowing in transmission but now is in the second stage. A reflected signal that's in the first stage, and a reflected signal that's in a second stage. You can start to see that I'm adopting some nomenclature that I can scale, both in terms of the forward versus the back, or the transmitted versus the reflected, stage 1, stage 2, all the way up to 3, 4, 5, 6, 7, 8, 9, however many stages I feel I want to do. Whatever order filter I want to do whatever to increase my sharpness of my bandpass behavior by adding more poles and zeros. This is terminology that until about about 2 decades ago was not generally applied to electromagnetics, not generally applied to optics. Okay, no one ever talked about the poles of a Fabry-Pro-Etalon. Okay, but they were there. They were always there, and no one ever noticed it. So here's the equations of state for. And again, these are just the algebraic equations, and I write these in order to eliminate the intermediate variables, so that I can get the output in terms of the input, or rather the outputs. Where are you? In terms of the input. Okay? And again, I can generalize on this. The nice thing about the notation that we worked through, the reflected waves in 1, the transmitted waves in stage 1, is we can now get general equations of motion, so I don't have to write them all down all the time. Okay? All this lecture is on my website, so you can download it and see it anytime you want. If you do solve it by algebra, remind you of Cramer's rule. That's a matrix form. Input-output vectors. There's the governing matrix in Cramer's rule. Find the determinant of it. And out pops the transfer function. And again, I can write this transfer function in something called the continued fraction form. You can see I have a fraction here, and then I have another fraction coming up in here. I've got a fraction here, here, and here. And as I add more stages, I'll get more fractions in the numerator and the denominator. So as I add more stages, the continued fractions just kind of keep building. Okay? Mathematicians love that. Engineers think that it's kind of cute, but can't really do much with it. You run out of paper, for one thing. So you write them in rational form, where you just put everything on top of a common denominator. And again, what you have here is a numerator that gives you a numerator that gives you zeros, and a denominator that gives you poles. Okay? So, classic DSP-1. How many of you have taken DSP-1? I really recommend it. It makes a perfect match to electromagnetics. Let's face it, a lot of what you're going to do with your electromagnetic signal is going to entail signal processing anyway. So if you make a measurement and then you do DSP, you want DSP-1. And then if you want to analyze all these different electromagnetic structures, then this is the way to do that, is to take the principles of DSP-1 and imprint them, the delays, imprint them on your transmission lines or your etalons or your structures and so on. Okay? So tremendously powerful set of tools once you make this into this pedagogical leap of recognizing the time of flight from one end of a transmission then to the end of a transmission line as a z to the minus 1 or 2 or 10 or k coefficient of delay. Okay? Keep going with this example a little bit. If I'm careless and sloppy about my relative reflection coefficients and transmission coefficients, I get a filter response that's really ugly. Okay? You can see there's some resonance behavior, but it's really, horrible. And what should happen is we should figure out a way to move these poles out over to there so that they fall on top of each other. Okay? And that can actually be done. It can be done in a variety of ways. One way to do it is to go into MATLAB and force it to do the work. Certainly nothing wrong with that. But again, it's kind of more fun to do algebra, pencil and paper. And so here's the location of the resonant peaks. Here's the transmission function as a function of omega. And what I've done is I've gone through the e to the I delta and then did the Euler's relationship, so I was able to pull out these cosine terms. And now you can start to see what, in fact, the polynomial means. Okay? So here's my transmission function. Here's my transmission function as a function of the frequencies. I have I differentiate it because the top. Let's face it, the top of that peak is a 0. Goes, it has a 0 slope. So I differentiate it to find the top of the peak, and I solve for that maximum frequency. And then I say, well, for a single resonant peak, I want the numerator here to equal the denominator there, and that way I'm going to always put my two peaks on top, those two peaks on top of each other. And when I do that, there's my cleaned up transfer function. Okay? Where now I have a nice, because I have the extra element and the extra stage, and I've properly designed it, I have a much higher quality factor for my bandpass filter. And I can keep playing this game by adding more and more and more layers. Okay? Here's that resonance condition plotted as a contour plot. So I have R 2, 3 in the middle. I have R at one end, I have R at the other end, and here's my R in the middle. So if I pick a particular R on the output, take another R on the input, I read across, and I find out what the third reflection coefficient should be for the middle. And that's how I know that I've satisfied both of those poles on top of each other. Okay? Again, we can write this as a state variable description, or even better in matrix form. And once I have this transfer function matrix, I can load this into MATLAB and I can do anything I want with it, invert it, or what have you. I will point out the interesting thing is that it's a big matrix, but it's very sparsely populated. And in fact, if you look carefully at it, you see patterns. So you don't even have to do the algebra. When we extended this to a huge field of these structures, we wouldn't even consider the algebra. We would consider the patterns of this governing matrix, and we would just populate the patterns of the governing matrix directly, and then work with it. Okay, very, very, very liberating to get away from all that algebra and input directly into MATLAB. Okay. So we have the output equations, matrix form. This is all state space. If you do control systems, this is all recasting everything what we just did in terms of the control system plant equations. And then I want to show you this transfer function. Remember I said you can continue to add these stages? Well, this is done in what is called as a thin film, a dielectric thin film coating on top of a sheet of glass for, say, anti-reflection or for high reflectivity. And in this particular case, this is designed to give you a very, very, very sharp and narrow peak at a particular wavelength. See, it gets very, very close to 1. Very, 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 very sharp, high reflectivity, high bandwidth filter. And this is a well-known description of how you do it. It's a stack of a high index, low index, high index, 2 low index, a high index, low index, and a high index filter that took the guys who designed this in the 1950s a tremendous amount of time thinking through their Smith charts and thinking through exactly how they had to line up their sines and cosines. And it's absolutely trivial to analyze using this algebra, this technique. Okay, and typical. You need materials to get there: zinc selenide and mag fluoride for your high index and your low index. And what you do is you put your plate of glass in a vacuum chamber. You have a boat of zinc sulfide, a boat of mag fluoride. You heat up one, it evaporates and sputters onto it. You do some calibration so you know exactly how thick that layer is. You stop it. You fire up the other one. You go back and forth between those two to create your high-low. You can imagine the precision of the manufacturing. You can imagine the weeks that it takes to calibrate and to start that process flow. Thin film filters came about in the 1950s when complicated optical systems were needed by the military, frankly, for being able to aim rifles and guns and stuff at other people and other boats and stuff like that. So they identified the losses due to the reflection off of a bare surface of glass as being prohibitive to the scale up, and so they invested in a lot of technology to do these thin film coatings. The trick is it's such a great technology. It led to the laser. It led to a variety of new optical devices. You couldn't build your smartphone display without it. So it's a really fundamental building block technology that was identified and driven. And for the longest time, the experts of those was in a company called Optical Coating Optical Coating Research Laboratory, I think, Incorporated. And so they out in California. It was bought by JDS Uniphase about a decade and a half ago. Okay, so and thin film filters are easily procured, a few $100s a run, current prices. Okay, but again, all built around this, this algebra that I'm showing you, easily lends itself to that kind of design as well. Okay, so big, long transmission lines, coupled waveguides, and what have you. Plates of glass, and then down to the nanometer layer of thin film coatings. Okay, very very wide range of application. And remember I told you I like the group delay. You see that you get the high resonance, the high Q, only for the frequency that spends a lot of time in the structure. Okay. So all the terms that you need, all those terms to add up, to stick around, so that they bleed out and they add up. And that's something that you learn from the group delay that I don't know if it's as apparent when you're looking at the phase response. Okay. Again, those of you who have taken DSP-1 will recognize this not as a Smith chart, but as a pole zero diagram. So the locations of where the poles are matter. And in fact, when you get good at this, you even start thinking in terms of moving your poles around to affect your filter response. Right? So again, all that stuff is buried right in your equation. By the way I like to do it is, the way I like to think about this is, you come in on your axis, and at any point on your axis, your denominator is the sum of the lengths to every one of those poles. Okay? So those lengths distances are all terms in your denominator. And so as you sweep through your frequency here, your relative amounts are changing and canceling and so on. Again, all tricks from another part of electrical engineering that belong in electromagnetics of these kinds of designs. Okay? It can get more complicated if you want. You remember those forward and back equations? Well, we can rearrange them so that we have coefficients of a 2x2 matrix with a vector for going from one stage to the next stage. Okay, so this is like it's sort of a strange analogy to a discrete a discretized transmission line, but now it's lumped for the entire transmission line as we go from one to the next to the next to the next. So we have an interface, and then we have the delays embedded in that matrix, that scattering matrix. And so by keeping track of all those scattering matrices and multiplying them together, we have some indexing issues at one end, not a big deal. But you can see that we can write for an arbitrary number of layers. Each of these phis is a 2x2 transfer function, 2x2 matrix. Okay, and the matrix and the cute thing about this is a compact matrix. It's only 2x2. The price you pay is that the coefficients become very, very, very complicated. Okay? And so there's a trade-off between a small matrix that has all the information cram-packed into it versus a very sparse matrix where you've unfolded everything. Okay? And I kind of, after doing this for a long time, I kind of like the latter approach. Okay? But this approach is layered media, scattering. It even gets into geosciences and things of that nature. Okay, and there's algorithms that relate to the design and analysis of all of these. Okay, and I won't go through too much of these, but you can turn them into analysis or synthesis. It's design and solve for everything. Again with MATLAB, and again what you're doing is you're moving the poles as you adjust your reflection coefficients of each one of those stages. Whoops. Sorry. Okay, so as an example, supposing you wanted to synthesize that rather arbitrary expression, you could go ahead and move your poles around until you iterate in on exactly the transmission function that you want from that. Okay, and there it is in reflection. So again, all this stuff can be ported into MATLAB. You can turn arbitrary responses into nice Butterworth filters. All this basic filter stuff now becomes realizable in the optics domain. And just so this was adopted very, very quickly in industry. It turned out the first papers on this were published in, let's say, 94 to 96. And by 98 and 99, I was walking through JDS Uniphase where I happened to be working, and I saw tons and tons of engineers doing their filter design, their structure design with MATLAB, all using exactly these techniques. I had there was a company in town called Quorum, and they did filter design, but based on birefringent filters, birefringent elements. And again, their structure, they took a look at this stuff, and they said that's exactly where we got it from. So this is all an interesting bit of research where you connect the dots and you unleash all the tools in one set of study into a field that at that time just wanted it and didn't know that it was out there. So that's what I meant when I said, Smith charts are really nice, they're interesting. They're not hard to derive. They're fun to do problems, but there's a very limited class of problems with which you can solve. If you start to have too many of these links of transmission lines where the feedback is too structured, you'll go nuts spinning around and around and around your Smith chart. And by the way, that's only at one frequency. This approach suited to MATLAB. You're already good at MATLAB. this is a much cleaner, nicer way to do those kinds of electromagnetic problems.